Thank you very much for having me at this conference. So the title is here. This is, let me just mention this. This is joint work with Groechenig and Paul Ziegler. So as it is, the story has little to nothing to do actually with model theory. So it's purely application, if you like. And so I'm going to start. The main theme is very similar. I don't know if you know this result of Batyrev, who used p-adic integration to show that birational Calabi-Yaos have the same Betti numbers. And the story is roughly the same. We have two varieties. These are these moduli spaces of Higgs bundles, and for some, for many reasons, one should believe that these two varieties are closely connected. They should be somehow dual to each other, and we're going to show that they have the same Betti numbers or Hodge numbers, so as Batyrev, and we also use p-adic integration to do so. So you could also probably replace this with motivic. Let me just say this now, motivic. This is sort of what we are trying to understand with François right now. And it probably works. I will point out through the talk where it's not entirely obvious how to do this, and I'll say a few words where the problems start. So let me start with the geometry of the problem, explain a bit where this comes from and why one cares. So K will, for now, just be a field, maybe of characteristic 0 or P sufficiently large. I don't want to get into like small problems. And C over K should be a smooth projective curve of genus bigger than or equal to 2. I denote by K of C the canonical bundle. And then the main objects which lead to the main objects for these moduli spaces are Higgs bundles. So we will actually, maybe I should have said this. The proof of the theorem is somehow much easier than the theorem than to state the theorem itself. But nevertheless, I should give a more or less complete statement at some point. So I'm going to define Higgs bundles, say a few words about them, but you can more or less treat them as a black box for the proof of the theorem. So a Higgs bundle, or maybe a rank n Higgs bundle, is a pair. That's the definition. E, phi, where E over the curve is a rank n vector bundle. And I write it here. Phi is a global section of the endomorphism bundle of E. And E twisted with the canonical bundle C. Okay. So they were introduced by Hitchin originally and somehow studying solutions to certain differential equations. But there's a very sort of naive way to look at them, which I like very much as a first introduction, is if you don't have a curve, say, and you just look over a point, then what is a vector bundle is just a vector space, and this guy is just an endomorphism of that vector space. So somehow over each point of the curve, you have a vector space and an endomorphism of that space, and you let vary that over the curve, over some algebraic curve, to get an interesting family. And to make the whole thing non-trivial, you should not just look at endomorphisms, because you will have very few. So you should allow you should allow some zeros of that endomorphism, so you get an interesting structure there. And indeed, so then what one usually studies are not one at a time, but all of them together, and pack them in a moduli space. So in this case, this is what one would call a GLn Higgs bundle. So in general, one can define a G Higgs bundle for any reductive group. And the slogan somehow, or the, how do you say? Yeah, let me just write. The slogan then is the following, that one has a duality on reductive groups, which is Langland's duality. So maybe split, but so Langland's duality. Which associates to G its dual. This is purely combinatorial. You have a group, you have its root system, you have roots and coroots, and you just switch the two. You get from one group to another. And so this Langland's duality is reflected as a geometric duality. And I mean, what I really should say is maybe mirror symmetry. But it's not a precise thing, mirror symmetry, at least for me. There's many different ways and incarnations of the same phenomena, but roughly, whenever you have this, you should have a geometric duality between moduli spaces. Of G and G hat Higgs bundles. And this is, this somehow justifies the definition of Higgs bundles. And it also, it's very usual that you have some combinatorial statement, or in this case a duality, which is kind of hard to handle. If I give you two dual groups, so for us, what's the case you want to look at? For us, G will just be SLn, and then the dual is PGLn. So these two groups, it's hard to go directly from one to the other somehow. Even though we have combinatorially, it's very easy. And then often it's good to introduce some geometric object, which you have more flexibility to handle. And this is the case here. So what I want to talk about is one incarnation of this geometric duality between the moduli spaces for SLn and PGLn Higgs bundles. And so this can be made quite explicit. I want to do now. So I'm going to introduce some more notation. I fix some integer n, some line bundle of degree d. And I want to define, so now I'm going to define this, M SLn L. So I want to look at the parameter space of all SLn Higgs bundles, but I'm sort of going to express it in terms of GLn Higgs bundles. This is actually easier. So there is, as I said, there's one geometric term, which should take semi-stable Higgs bundles E and phi. And one should then require that the determinant of E is isomorphic to our fixed line bundle L, and that the trace of phi is 0. So it's actually sufficient to think of phi as just being a matrix for the whole talk. And then the trace makes perfectly sense. Semi-stable this comes from the GIT thing, so otherwise you would get a stack here, and eventually we want to do p-adic integration on this space, so it's better to have a variety. And then there's the L. So if I would have chosen L to be the trivial bundle, then this just means that the determinant of E, we require this to be trivial, so it's an honest SLn bundle. And the trick to introduce an L, so that's the remark here, if D and N are co-prime, then I get that this is smooth. ML SLn is smooth quasi-projective. It's a smooth quasi-projective variety. Okay, this is so up to isomorphism. In general, some equivalence. So this is one of the spaces, and then there's the other one. It's the PGLn space. So now this one that depends on the line bundle we chose. This one will only depend on the degree. And again, it has a very natural definition in terms of just PGLn bundles that have a certain lift to a GLn bundle such that the degree of the GLn bundle is D. But for us, there's an easier definition, which is for practice. So I denote by gamma. Phi is endomorphism of E, yes, a tensor with the canonical bundle. Exactly, yes. So I give a direct definition of the PGLn space the following way. So I look at the Picard. This parameter is degree 0 line bundles on our base curve. And I look at the n torsion points. So as a group, this is just it's a finite group. It's a Z mod nz 2G copies. And I have an action of gamma on the SLn space by just tensoring the vector bundle by a line bundle. That gives him an action, and because it's n torsion, it will keep this. Exactly, yes, bigger than n. I think this is actually sufficient for. Right, so we have this action. I'll just define, sort of a bit lazy, this as the quotient of this. This comes to the same as the moduli theoretic description of the whole thing. So remark is here that it's the same as there. If D and N are co-prime, the action of gamma is not free, but I think what people call this is an orbifold, MD. So it's a quotient of something smooth by a finite group. That's the quotient singularities. Exactly, yes, yes. It is, yeah, as I said, it's easier to think of it as to see this, just think of it as PGLn bundles that lift to a GLn bundle whose degree is D. and then you get the same space. And that one obviously does not depend on that. Okay. Now, what's the point? So in the title is the Hitchin fibration, and this is the sort of the way the duality works geometrically. So let me explain this Hitchin fibration. So to a pair E, phi, so what it is, it's a vector bundle and an endomorphism. So locally, it's a vector space and a matrix. To a matrix, I can associate its characteristic polynomial. So that's what you do locally. You take the characteristic polynomial. Globally, how does this look? So I can do this for my spaces here, MLS. I will just abbreviate this by S. To me, the N will always be fixed. And here is MDP. So both have these HS and HP, these maps. So where does this characteristic polynomial live? I denote the base by A, and it's actually the direct sum 2 to N, and then it's global sections over the curve of the canonical bundle, tensor I. So if I put I equal 1, this corresponds to the trace of the endomorphism, and the trace is 0 by 1. So there is no. If I would look, so there's the same for the G. Just the GLn space has the same, and it would have the 1 there. So we get these morphisms. This is an affine space. It's just a vector space. Okay. And so how does this duality work? So this is a theorem now by Hausel. Hausel and Thaddeus, they say that the generic fibers of H, S, and HP, there are torsors and here's the duality, so for dual abelian varieties. And so there's one PS, which lives on the SLn side, and there is another abelian variety on the PGLn side.
I'm sorry, what are S and P?
S, so I want to just, this is this space. I just want to, it's SLn.
Oh, okay.
But it's going to be the same for all the talk. Yeah. Okay, so now, so there's two things. One is there's this duality, which really reflects the duality of the Langlands dual groups, but in a geometric way. So that we like a lot, because it's a much more flexible notion. And then there's a little headache that I'm going to just denote in red here, so torsors. So, and this headache, you can make it more explicit. It really comes from the fact that we want smooth things. So that we had this L and this D. If I put them 0 everywhere, it's actually, there's no torsor structure. There's actual dual abelian varieties. So I can have that, but then I need to cope with the singularities of my spaces. And so now we want to look at the topology of these spaces, so it's much better to be in the smooth setting. And so this will sort of pop up. Again, we have to pay the price, but for this talk, this might be a bit too technical to go in. So everywhere this appears, I'll just mark it red, and that's something I don't discuss in my talk, but it's there. So now we have this duality. This is some sort of mirror symmetry. So this is called SYZ mirror symmetry, this kind of duality. So this is Strominger, Ngão, and Zaslow, and they came up with the idea that you have two mirror partners. The way you pass from one to the other is that they should be fibered over a common base, and then the fibers are tori, dual tori, generically. And then, I mean, this idea is now, there's some non-Archimedean version. This is a very, very interesting field, but this came sort of before. I think it was the first non-trivial example of, sort of mathematical example of such spaces that appeared.
Dimension of A is combination of M's?
Sorry?
What's dimension of A, dimension of M's?
A's and M's. So A is half of the dimension of each of these spaces. So, I mean, they have the same dimension, but yeah. Right, this is an interesting aspect. So now that we have some sort of mirror symmetry, then Hausel and Thaddeus, they went on to see other manifestations of the duality in the topology of these spaces. So I mean, this maybe is more familiar. We have this symmetry of Hodge numbers usually in mirror partners. And so something like this should happen here too, they thought. And so I want to formulate this now. So I need some notation. So if I have a complex variety, I want to study its Hodge numbers, and a convenient way to study them is that I define a polynomial in two variables, x and y, which will have all the Hodge numbers at once, so, but with some cancellation, so h, p, q, and i of x, x to the p, y to the q, with h, c, p, q, I are compactly supported. Hodge numbers. So if I have any variety over C, its cohomology has this, in general, two extra filtrations, and they might not be pure. So you get, so P plus Q doesn't necessarily add up to I for a general variety. And so I could possibly lose some information because there's the -1. But so here is so that's the bad thing. The good thing is that we have this. So if I have U in X open, then E of X, XY, so it's actually, this way we get the realization of the K0 varieties of the Groechenig ring. So this is what makes it very handy. And the second thing that is useful in this is that our spaces will what's called it is pure. So our spaces are pure, i.e. I have that H, C, P, Q, I is 0 unless P plus Q equals I. And then you see I don't get any cancel. I get all, so somehow this polynomial, in this case, controls all the things. Now, so the duality it's very funny, is inspired from physics, but also there's another issue here with the fact that the PGLn space is not smooth, but it has orbifold singularities. And that also appeared already in physics before, that you could start with some smooth projective Calabi-Yau, and you end up with its dual being not smooth, having orbifold singularities. And then Batyrev remarked that in this case, there is no symmetry between the Hodge numbers. They don't even agree. In fact, sort of the singular guy, the Hodge numbers are too small. And so he came up with a way of recovering the missing pieces, and that's what's called stringy Hodge numbers, or in this case, it's going to be the stringy E polynomial. So in this case, I will assume that, say, M is smooth, as for us, and gamma acting on M, some finite group. Gamma M is finite. And then I consider the following. So this is now what is called the stringy E polynomial of M divided by gamma. It's a two-variable polynomial, and it's a sum over usual E polynomials. So I would sum over all conjugacy classes, and I consider the space. So for each, I pick some representative. I look at all the points that are fixed by this single element. It still has an action by the centralizer of gamma, and that's the E polynomial I look like, I consider. And then I sum up, and there's some correction term here. So what is C of gamma is the centralizer. And F is some factor. This is sometimes called the fermionic shift, which it doesn't play a role for us. But there is some way to deal with these quotient singularities. Is to the power, so in general, it's now not a polynomial. It's F of gamma. And F of gamma is a number I have not defined. It's some rational number you can associate. And so that's all. I think Batyrev remarked that for toric varieties, this fixes this problem of having too small Hodge numbers. And so Hausel and Thaddeus were inspired by this, and they made the following conjecture. This is Hausel, which is now, I mean, now it's a theorem. So by Groechenig, by us. Stating that if I take the E polynomial of the SLn guy, which is smooth, this is the same as the stringy E polynomial of the PGLn guy. Almost. Now, as I said, there's the torsor. So here, it's not even just a stringy thing, but it has some extra condition coming from the L. Let me just say in words, the idea is, so to be precise, so AL is explicit, some explicit gerb, mu. And in words, I'd say one more thing about it. So it's some object with coefficients in mu n. It will induce on each of these factors a local system. And then you just take homology in that local system instead of just the invariant homology. But it's really explicit in the sense that, so the conjecture was actually proven by, verified by Hausel and Thaddeus in their paper for rank 2 and 3 by hand. So they just computed all the terms, and they got some huge expressions, but they agreed. And so that's the intriguing thing. And so now, I want to say some words about the proof, which now should be much easier. We're going to reduce it step by step to some p-adic integrals. So let's this? Let's see. So for some general remark, so for x a variety over fq, so it's now a finite field with q elements, we define so for a thing with, what do I want to say? For a variety over a finite field, the role of the E polynomial, where is it there? Is really E x x y. That's why we like it. It's really, it corresponds to the number of points of the variety FQ rational points. This is sort of the analog. And so similarly, you can define the stringy thing the same way by just replacing everywhere where you see an E, you replace it by counting. And everywhere you see, so x, y, you should just replace by the order of the finite field Q.
Is the data material Q somehow interpretation for the rational number phi of gamma in terms of the singularity? Or?
For which one? For this?
Yes, in terms of the singularity, do you have an interpretation?
It's very concrete.
Yeah.
I don't know you don't
So you can write down.
Oh, sorry, yeah. I mean, this is a formula. You somehow look at the action on the tangent space, and you look at the eigenvalues. Yeah. It's not just
Comes the interpretation here.
the same definition, just over the algebraic closure of the finite field. Yeah. Right. Sorry, this is not some mystery. It just takes some time to write down. Okay, so just replace everything. You get these two notions. And now you want to go from one to the other. So, and this you can. So by a theorem of Katz, the conjecture follows from proving the following, namely that the number of points of MLS FQ equals the number of stringy points of M, P, FQ, where again there is this part which is a bit mysterious that comes in. And so a priori I haven't defined you these spaces over a finite field, but at the beginning I choose K to be any field. So I can, if I choose K at the beginning to be a finite field and my curve is defined over a finite field, I just take the moduli spaces I get over the finite field. And then everywhere but from some bad primes, they sort of behave well and they give you this. So this follows from this, of course, for I mean, sufficiently many Qs. It's not, you have to sort of have to be able to, at some point for every Q, it should be true. Okay, so that's. Right, so it's the same. You will have a local system on these guys, and instead of just counting, you will take the trace of Frobenius at each rational point of that local system. It's sort of it's what this Groechenig-Lefschetz trace formula just tells you to do. There's no real choice you have. Yeah, it's some right. It's instead of counting, it's some sort of character sum that you will get.
So when you say for many Q, that means Q.
Right.
Q is not for the same P. Yes.
No, exactly. So it should be true for almost all P, but then it doesn't have to be true for the FP. But in each P, you can also after a finite step. Okay, so now we have a counting thing, and then as Batyrev, we want to translate this now in an integral problem, in a problem about p-adic integrals. And that's where really the magic somehow starts to happen, because for now it doesn't really simplify anything. So F is going to be some local field. So it could be f, could be a finite extension of qp. Well, actually, it doesn't really matter. It could also be a finite extension of fqt. So this doesn't even play a role. O of f is going to be the ring of integers. And what is k of f? Fq is going to be the residue field. Then now I just assume that you're much more comfortable with p-adic numbers than with all what, and you just all know p-adic integration more or less. So you can, if I have some variety over O of f, I look at its points. This is sort of, in a naive sense, a p-adic manifold. And if I have some differential form, not as in the talk we saw before, just on the nose, you take an honest differential form and just integrate it. You get some real number. And that's what I understand with p-adic integration. And so in our case, so for us, we take now our curve to be defined over O of f. You get the moduli space, which now lives over O of f. And I take omega, some global volume form on M, L, S, which is now defined over O of f. So this I haven't said, but this guy is actually symplectic in particular. So it's always Calabi-Yau. And so we take something that trivializes the canonical bundle.
When you say C over, do you think it's smooth?
Yes, yes, yes. Yeah. Same conditions as in the, yeah, right. And now it's not a field anymore. It's okay. And then by a theorem of Weil, which well, is really very fundamental in this whole topic, is that if I take now the p-adic integral of my space, S of f, over any volume form, then what I get is just the number of points of n. That q to the dimension of. And this is a finite field. So, okay. So if you have, so this is not just true for moduli spaces of Higgs bundles. This is actually it's true for any smooth. Anything that's smooth over O of f, it will have a formula like this, which just comes essentially from Hensel's lemma, that you have a rational point, you can lift it to a little ball in your p-adic manifold, and then locally it gives you, so each point will have volume 1 over q to the dimension, and then you just add up all the points. So it's nothing, it's not deep, but it's very useful. So this takes care of one side of the conjecture, which is, but not the other. And how does the other one go? It's more, it's more complicated. But so in fact, the volume form we chose, it descends. To form a omega bar on M dp, now also defined over O of f. This is just because the gamma action, it will leave the canonical bundle invariant, and so you get a form below. And by, well, let's say by work of, again, Batyrev in this stringy setting, but really important for us is this work of Denef and Loeser. We can also look at this integral now, M d p O of f omega bar, and it will give you the stringy count. of this guy. K of f, again, divided by q to the dimension. And this is sort of the most surprising part in this story for me. How can it? I mean, this stringy thing it has a very weird definition. It's a sum of conjugacy classes and all. And sort of the p-adic formalism takes care of all of that. From this point of view, it doesn't look different than the smooth thing. It's really the same thing, and it just all the right things happen. It's coming. Right, so it's almost good. So if I have the alpha here, so what I said before, it's like a character sum. And sort of naively, if you take the restriction to the finite field, here you have some character that you should integrate, and just pull it back. Gives you some function here that you have to integrate to make this work. And so now, so this was already in the literature, all of this, and now we are supposed to compare these two integrals, and that, well, we use the Hitchin fibration to compare the integrals. So in fact, it's enough to prove the following. Let me make this a bit bigger. So I just want to compare these two integrals now fiber by fiber relative to the Hitchin base. But now the p-adic formalism allows me to not have to look at all the fibers. So these would be all the fibers I have to check. But I can assume that sort of generically, the generic point of my p-adic disk, it lies in this generic locus. So this is the generic locus of the Hausel-Thaddeus theorem. That's where the fiber is smooth, p-adically smooth. Okay? So because the complement will be all the things that lie entirely in this in a subvariety of smaller dimension. And this has volume 0. So for any such thing, I'm not just left to prove this. So I take H S inverse of A. Here I get I get the volume form that I get on the fiber. I have to integrate. And here is the same HP inverse of A. I also get the volume form on the fiber, and the function just restricts. Here. And now this is looking good. Now we have two integrals which are over abelian varieties over some local field, and we should try to understand them. So notice that there is still a quotient morphism like this. Just quotienting by gamma. And now these are both torsors over abelian varieties, but now over local field. So there are two cases. So the first case is, there's a trivial case. If this is an honest torsor, it will have no rational points over F. And then because this one cannot have either, because there is an actual morphism like this. And then 0 is equal to 0, and that's fine. So the first case is when this fiber, so H inverse E of A of F is non-empty, but the other fiber is empty. Okay, so then this guy is 0, and I have to argue that this one is 0. Now I cannot, because I haven't really told you what f of L is, but it turns out that this function, which I now can see as a function on the f points of the abelian variety to, say, C, is a non-trivial character. And if you integrate some non-trivial character, over group, you get 0. So in this case, is 0, which is what we wanted because the other side is 0 trivially. And so finally, we're just in the case when both guys are non-zero. Non-empty. This is not equal to HS. And in this case, this is also haven't discussed, but in this case, this is not so hard to see that then we have no character. It's just 1. And we have to then prove the following. This follows from the following proposition, the equality. So, and this is something which is really true general. That's why I didn't really describe the abelian varieties any further. So let phi v be, so this is defined over some local field, be an isogeny. With kernel. So what I want the order of the kernel of phi to be a coprime to the thing. Then for any volume form, omega on B, we have that the integral over A of the pullback of omega is the same as the integral over B of omega, over the F points. Okay. So this is not entirely trivial because the phi doesn't induce a surjection on the F rational points a priori. So the image of phi of this set will be strictly smaller, and you have to somehow see that the kernel and the co-kernel have the same size. How much time do I have?
2 or 3 minutes.
Okay, okay. So then, yeah, it's not true, I think, if A and B are not dual. So one way one can prove this is to pass to Néron models and use Weil's theorem again. So it's basically you have to compare the count of the Néron models and to use the Groechenig pairing on the components to get the thing. Okay, so in the last 2 minutes, I want to say something about the general case. So in the general case, in general, I have something like mg and mg dual for 2 reductive groups. Now these are stacks, and we don't know how to integrate on them in general, but they also are fibered over the same base. And everything I said about duality of fibers with tori is still true by work of Donagi, Pantev, and Cheng and Su. It's a beautiful, very general story in representation theory, basically. And if I restrict myself to some, so this is the anisotropic locus, which lives in between this generic locus, but it's better than the whole base. So if I look over this space, in general, so these are orbifolds, or are again orbifolds. And so the generic fibers are again dual tori. And so the same argument that I just did, fiber by fiber, it will tell you that the stringy point count, so now both sides will be stringy, that they have to be the same. But no, a priori is no twists in this case. And then if you spell out, so this the stringy contribution is given in terms of what is called endoscopic data. So this was remarked also by, I think, physicists, like in the paper of Frenkel and Witten, but this has never really been spelled out, but sort of the automorphisms, they come from endoscopic data. And with introducing again some red things here and here, you can isolate certain parts of each side and compare them. And so this is about to be written up now. You will get a new proof of this geometric stabilization that was used in the proof of the fundamental lemma of Ng鸽. And so this gives a direct proof using p-adic integration of a p-adic identity, so of orbital integrals, but somehow on a very different space. And so I know that there is a lot of work by Hales and Julia Gordon and others studying this using model theory, so that would maybe be the intersection point, the closest intersection point I see that I have with this conference, and I would be very happy to discuss this any further. Thank you. That's it.